I'm going to talk about 3 different ways of using work and energy to solve physics problems, and then I'm going to recommend one of those ways. If you are just starting out learning about work and energy, you may find this presentation to be a little abstract, not much use in solving actual problems. But if you've been studying this stuff for a while, you may find that this is just what you need to help put the pieces together. So here are 2 possible methods for solving problems. Work-energy theorem, of course, work done on a system is equal to the change in kinetic energy. That's the short version of the equation. Slightly longer version looks like this. Work done equals the final kinetic energy minus the initial kinetic energy. Over here we have the law of conservation of energy. Initial energy equals final energy. Start out with a certain amount of energy. A while later, you've got the same amount of energy. Here's the long version of the same equation. Initial kinetic energy plus initial potential energy equals final kinetic energy plus final potential energy, using the letter U for potential energy. Each of these approaches to solving problems has advantages and disadvantages. The advantage of the work-energy theorem is that it always works. If it's possible to use work and energy to solve the particular problem you're dealing with, then the work-energy theorem will find the solution. The disadvantage of this is that it uses work, and work is a notoriously difficult, confusing topic. People really don't like using work for that reason. We try to avoid using it if we can. Sometimes we can't, but I don't recommend using the work-energy theorem for this reason. I never use it. The only reason I think to use it is if your professor insists that you use it and tells you to use it to solve a particular problem. Now over here, the law of conservation of energy has the advantage of there is no work. Instead of work, we have potential energy. And potential energy and work are 2 different ways of addressing the same thing, namely how forces affect energy. So potential energy in a way is almost a duplicate of work, but not quite. But the real advantage of potential energy is just that it's easier to work with. For some reason, people are just less prone to making mistakes with potential energy, and that's really why it was invented in the first place, I think. It's just a better, more reliable way of dealing with work when possible. Now, the disadvantage of law of conservation of energy, unfortunately, is that it does not always work because energy is not always conserved. Now, I know you probably heard somewhere that energy can be neither created nor destroyed, so energy is always conserved, and yes, that's true in principle. But when you're solving a problem that relates to a particular physical system, the energy in that system doesn't have to be conserved. It's possible to bring in extra energy from somewhere outside the system to add to it, or it can lose energy. The energy can leave the system and go elsewhere. So energy is not necessarily conserved. If the energy is conserved, which it often is, then this works great. And if it's not conserved, well then, you could use this, but fortunately there is a better way. Now I'm going to repeat some of what I just said in slightly different terminology. The work-energy theorem is valid for all forces, both conservative and non-conservative forces. And I'll tell you what that means in a minute. If you have 1, 2, 3, a whole lot of forces, some of them would be conservative and some will be non-conservative. It doesn't matter. You calculate the work done by each one of those forces, add it all up, and put it all right into that W, and you've got yourself a valid formula that will give you a correct answer. The law of conservation of energy, on the other hand, is only valid when all of the forces involved in the problem are conservative forces. And again, you might have 1 or several conservative forces. As long as they're all conservative, this will work. As soon as you bring in a single non-conservative force, forget it, this is wrong. You've got to do something else. So what is a conservative force? Well, a conservative force is just a force that conserves energy. And here are a couple of examples of familiar conservative forces. The gravity force and the elastic force, also known as the Springs force or the Hooke's law force. There's the force of gravity, there's the spring force, and then here's the potential energy for gravity, there's the potential energy for the elastic force. And these are things that you would substitute in place of the U in that other equation if you were using them. Now, some non-conservative forces. Here are a couple of more familiar ones. Friction, both kinetic and static friction, is a non-conservative force, and also air resistance. There's a couple of different versions of this formula. Sometimes you see the short version with just a constant times velocity, but in either case, these are non-conservative forces. Energy is not conserved, and for that reason, I didn't write down a formula for potential energy for these. Unlike here, you can see there's potential energy for gravity and elastic. I didn't write potential energy formulas for these because there are no potential energy formulas for these forces. Non-conservative forces simply cannot be expressed in terms of potential energy, so there's no way to do that. Now, there's certainly other conservative and non-conservative forces besides the two sets there that I just showed you, but the principle is still the same. So I said I was going to show you a third way of doing things, and here it is right here. Here's the short version. Initial energy plus work done equals final energy. There's the long version. It's just exactly what you would think. Kinetic potential work, kinetic potential. So how is this different or better than any of these other ways that we've looked at already? Well, okay, for starters, you can see a definite connection between conservation of energy and this equation down here. In fact, if the W was just equal to 0 in these equations, then they would be exactly the same as those conservation of energy formulas right up there. So you can see then that energy conservation is a special case of this. So this is a more general case that includes this as one possibility. It's not so clear the connection between this formula and the work energy theorem. If you make a comparison between the two, you can see some things in common. There's a KF and a KF, a KI and a KI. There's a W, there's a W, there's a couple of U's. Where are the U's up here? It doesn't look at first glance like these are two versions of the same thing, but in a sense they are, because they are both general formulas for solving work energy problems where it doesn't matter whether energy is conserved or not. So how can we resolve this apparent contradiction that these look so different? Well, here's how. This W and this W are not the same W. I repeat, this W is a different W than that W right there. This W is the work done by all forces, both conservative forces and non-conservative forces. If you've got 5 forces, you're going to have to calculate work for 5 different forces and add all that up and put all that right into here to get an answer. This W is not the work done by all forces. This is only the work done by non-conservative forces. The conservative forces are taken care of by the potential energy formulas. So if you've got several forces involved in your problem, well, some of them will go into the W and some of them will go into the potential energy, most likely. Now you can see right away that there's really no way that this could be the work done by a conservative force, because a conservative force is going to automatically conserve energy. Initial energy equals final energy, and in this case that could only be true if this W is equal to 0. Now, conservative forces don't have to do 0 work. Very often they don't do 0 work. But the way that's taken care of is by the potential energy formulas. So the only time that this W is going to not be 0 is if there are non-conservative forces. The result might be positive work is being done, in which case W is positive, and so the final energy would be greater than the initial energy. Might be that negative work is being done on the system, in which case the final energy will be less than the initial energy. So this is the method that I recommend, And people have asked me, what is this called? And to tell you the truth, I don't think it has a name. I've seen it referred to actually as the work energy theorem sometimes, and in a way it's a rewritten version of it, but if you look up the work energy theorem in a book or a website, it's going to tell you this, not this. So I don't know if it's really called anything. There's actually several different ways that you can juggle these formulas together, and I think this is the best one right here. Now, what you should take away from all of this is really just this last line. If you're making yourself a cheat sheet, all you need is this one last line. This includes everything you need that I've talked about up here. Obviously, that's not the only thing you need. You need some potential energy formulas and maybe a couple of equations for work and, of course, other things. But ultimately, this last line is all you really need. And there's also another way if this doesn't work for you. The way that I actually remember this is this way. This is just an alternative version of the same thing. Energy equals kinetic energy plus potential energy, and then again, initial energy plus work done by non-conservative forces equals final energy. So in my mind, this works better, and I think you can see pretty easily that these two together are equivalent to this last line right here. So take your pick, either one.